everyone, my name is Apeksha S. Redder, currently pursuing aerospace at BMS College of Engineering. In this presentation, I will walk you through my computation fluid dynamics study carried out on Sukhoi Su-27 fighter aircraft using Altair SimLab. The goal was to understand how CFD can be used to analyze aerodynamics in high-performance aircraft. Study primarily focused on the external aerodynamics of Sukhoi aircraft. Using CFD, I aim to visualize airflow patterns, understand how the geometry of the aircraft interacts with the free stream, and compute key aerodynamic coefficients. The objectives are to visualize airflow around the aircraft, to study pressure and velocity, to identify critical flow features such as separation zones and wakes, which influence drag and stability. Together, these objectives provide a complete aerodynamic picture of the aircraft. The aircraft geometry was first prepared by importing it in step format. Since high fidelity models can be computationally expensive, I scaled the model down to 0.4 times the original size and simplified unnecessary features. The computational domain was created using a bounding box, ensuring sufficient clearance between the aircraft and the domain boundaries to avoid artificial interference. For meshing, I applied an unstructured mesh with tetrahedral elements in the main volume and prism layers near the surface. The prism layers are important for capturing the boundary layer accurately, which directly affects the drag prediction. Velocity field analysis. Here we can see that the velocity contours over the wings and the fuselage, airflow accelerates significantly, shown in the red and the yellow regions, which indicates higher velocity. This is the consistent with aerodynamic theory, where the curved surface speed up the flow and create lift. Behind the aircraft, the wake is clearly visible in blue and the green regions. This is a low velocity wake, which represents energy loss and drag. The fact that the simulation captured both lift generating acceleration and drag producing wake show that the model is physically consistent. Turbulence analysis. Turbulence modeling is a crucial part of CFD. The parameter is used to judge how well the mesh revolves around the near wall region of the flow. Ideally, depending on the turbulence model, turbulence should either be in the range 30 to 300 for wall functions or less than 1 for resolving the viscous sublayer directly. In my case, the values went a little high, which is clearly indicates that the mesh was too coarse near the surface. Pressure field analysis. The pressure distribution provides another way to confirm aerodynamic principles. High pressure zones are visible at the nose and leading edges of the wing, which are stagnation points where airflow slows down. Low pressure zones are seen on the upper surface of the wings and fuselage, where the airflow accelerates. The difference between these high and low pressures is exactly what generates lift on the aircraft wing. This result reinforces the reliability of the CFD approach, even with the limitations in turbulence modeling. To conclude, the CFD study successfully validated the basic lift and drag mechanisms of Sukhoi aircraft. The simulation captured airflow acceleration, pressure differences, and wake formation, all of which are essential aerodynamic features. For future work, I plan to refine the mesh to achieve turbulence values in the appropriate range. This would allow more accurate predictions of skin friction drag and flow separation and overall aerodynamic coefficients. In summary, this project gave me a strong understanding of applying CFD tools like Altair SimLab to real aerospace problems and highlighted the importance of mesh quality in computational aerodynamics. Thank you.